For this design criteria lesson, we're going to carry on with part 4 of our component selection. After completing this lesson, you'll be able to compare video components and options and make informed design decisions. First, let's talk about the camera system parts that are spec'd out for this series. For the camera, we're using a Fat Shark 700 TVL CMOS camera that's capable of NTSC and PAL. For video transmission from the quadcopter down to the ground, we're using a SkyZone TS5823. For the monitor and receiver, we have a 7-inch 1024 by 600 monitor that's made by FieldView. So first, let's talk about the camera. So the Fat Shark 700 TVL CMOS camera, this is a good system because it has a few things going for it. The CMOS type camera is lightweight, it has low power consumption, and because of the technology is fairly inexpensive. The specific unit has a few extra things going for it. It has removable lenses so we can change the field of view, and it also comes with a pan and tilt servo already built into it. Now in our case we only need tilt, so I've deconstructed it a bit. I've taken off the pan servo and we've modified it slightly so that the servo is going to be held directly with our 3D print. When we're looking at cameras, there are a few things that we need to be concerned with. First of which is the type of camera. Now there is a CMOS and there's a CCD camera. Generally the CMOS cameras are going to be less expensive because of the technology, but they're also going to be lighter and have lower power consumption. While a CCD type camera, or really the chip that's on the camera, is going to be more stable, less receptive to interference in the lines, but because of this it's actually going to be heavier, it's going to use more power. Because we're completely concerned with power consumption and weight rather than the quality of the video, this is why we went with a CMOS camera. The 700 TVL is actually the number of lines on the image. The 700 TVL is actually a fairly high number, so we get a really good high quality color image out of this camera. For output, NTSC or PAL is selectable on this specific camera, so we can decide how we want to transmit the video. For video transmission, we need to take the camera signal and we need to send it back down to the ground. To do that, we're using a SkyZone TS5823. This is operating at 5.8 GHz and has 32 channels. This also allows us to send both audio and video. Now this has a few things going for it. First of all, it's small and it's lightweight. This is again important because it's our main focus to keep the overall system as light as possible to increase flight time. This specific unit, running at 5.8 GHz, will give us about a mile of range with no obstructions. So if we're flying in an open field or an open area where we don't have a lot of tree coverage or buildings, we can get a pretty good range to get our video signal back to us 1 mile away. This specific unit has a set of dip switches on the board that allow us to change the channel. So we're operating at 5.8 GHz, but we have up to 32 different channels that we can operate on. And this specific unit also comes with a cable that allows us to run it directly to a GoPro. So again, this goes back to being able to configure our system. If we want to run a GoPro camera, we can plug the micro USB that comes directly with this board and transmit both audio and video back down to the ground fairly easily. The nice thing about running a GoPro is it's got a self-contained SD card to store the video, and it also has an onboard battery. So we don't have to wire the GoPro up to the system, with the exception of sending the video back down to the ground with a live feed. And lastly, we have the monitor and receiver. Now the one we're using is a FieldView 777. And this is a great option because it already has a 5.8 GHz receiver with 32 channels on it. It's a 7-inch 1024 by 600 color monitor, and it also has audio capabilities. It has video in and video out, so we are able to send the video out of this monitor and record it on another device if needed. The specific one is fairly high resolution. It matches the 32 channels that we have on our transmitter. It's 2.4 GHz protected. And that means that the 2.4 gigahertz frequency we're operating at with our controller that sends the signals to the quadcopter that tells it to go up or down, pitch left or right, it's not going to affect the video quality at all because this specific one is isolated from the 2.4 gigahertz frequency. This monitor also has a built-in battery, and with a charge it can last up to 2 hours. And again, it does have audio capabilities as well as a headphone jack on the side. There are many different options that you have when you're trying to view the video on screen. Because we're building a similar type of quadcopter to an FPV or a first-person view quadcopter, there are plenty of on-the-shelf different types of goggle systems where you can get the 5.8 gigahertz signal directly to a set of goggles that you wear, so that way you can see exactly what you see from the quadcopter when flying. Now, the reason I chose to go with a monitor rather than a goggle setup is because the monitor can be viewed by somebody else fairly easily because it is a 7-inch monitor. It also allows us to fly line of sight with the pilot while somebody else is viewing the camera. So if you just have a set of goggles and a first-person view setup, then you're not going to be able to have anybody else look at the monitor or send the video signal out to another set of monitors to have more eyes looking at what we see on the ground. So again, this is a great option, fully self-contained unit, and if you search around online, you can find various prices for these that range from about $100 to $150. So overall, the camera system parts, let's talk about what we have. We have a lightweight camera and a transmission module. The Skyview TX module operates at 5.8 gigahertz and has 32 channels available. We have a high resolution, the 700 TVL color output camera. We can also swap out a GoPro camera, and we can transmit audio and video easily with the TX module that we chose. We're using options that have low power consumption. Because our camera is a CMOS chipset, it actually operates with lower power consumption than a higher quality CCD camera. Our camera is currently running at about 5 volts, while the transmission module is running between 7 to 24 volts. So there's a wide range of voltage that we can operate on, but we need to provide at least 7 volts to be able to transmit the video down. The good news is that the battery setup we're using is 11.1 volts or 14.8 volts. We're using a power distribution board, so we can automatically supply the voltage needed to both things. We also have camera tilt included with the camera that we chose. There are plenty of camera options on the market. Some automatically have the transmission modules built onto them, including antennas. So if you're looking to build your own system, don't think that you have to go with the cameras that we chose. If you want to use a fixed camera or if you want to build your own tilt setup, you can buy individual servos, you can buy specific cameras and transmitters, and you can pick and choose which components you want. You can very easily get away with using a GoPro that you have because we're planning our build so that we have enough capacity to lift a GoPro or additional equipment as needed. So that might be a great way to get a first-person view by using a fixed GoPro without including the tilt module, plug it directly into the transmission. So now let's talk a little bit about how we can get the camera to tilt. There are 2 different pieces of equipment that we can choose. One is a brushless gimbal motor, and this is very similar to what our propeller motors are going to be, and the other is a servo. Now each of these have pros and cons, and I just want to pinpoint a few things here. The gimbal motors are heavy, and generally they're only seen on higher capacity quadcopters or multi-rotors. They do offer smooth motion. Because they are brushless, they don't have notches or different areas where we're dealing with a gear reduction system and a stepper motor. They do unfortunately require additional parts. Generally, when you deal with a brushless gimbal motor or multiple gimbal motors, you will have its own controller. Now, the own controller will also have a similar type of ESC that we see when we're driving the motors that have our propellers and provide our lift. So keep in mind that if you decide to go with a gimbal setup on 1 or 2 axes, you're going to be adding probably an additional 200 grams in just the gimbal motors alone, plus you will need an extra circuit board that can help control that. However, with the servo motor, we generally have a fairly light package. We will get jerky motion because we do have a gear reduction inside of the servo, but it does plug directly into the CC3D. Now I do want to make an important note here. Gimbal motors are generally used for stabilization. Now you often see these on 2 or 3 axis rigs when somebody's running a high quality camera, whether it's a video or still camera, to make sure that they isolate the motion of the quadcopter and keep the camera stable. Now this is great if you're doing high quality photography or you really need that stable camera image. In our case, the weight is going to be more important than the jerky motion of the camera tilting. We are going to be using manual control of the servo, so we don't really need to worry about that smooth motion because we're going to be turning a dial on the controller to look down or up as needed with our camera. We can use automatic stabilization with our CC3D flight controller to control a servo to automatically tilt the camera up and down based on the angle that the quadcopter is flying at. So while we will get a little bit of jerky motion, we can achieve the same type of thing that a typical gimbal setup will require. However, we can do this without having additional equipment because we can send a 5-volt signal directly to the servo to control it without having any additional boards, IMUs, which are inertial measurement units, or any ESCs.